Hello and welcome to our webinar here at Glasgow Caledonian University. It is organized by the project Mainstreaming Innovation. My name is Branka Dimitrijevic and I will be moderating this webinar. I'm also directing the project Mainstreaming Innovation, which is a joint project of 9 Scottish universities led by Glasgow Caledonian University. It is funded by Scottish Government and it supports collaboration between Scottish businesses and universities in developing innovations for low-carbon infrastructure systems and their integration in the built environment. Before we continue with our webinar, just a few housekeeping points. If our webinar is interrupted by a fire alarm or there are some online disruptions, please try to join us later. You can start using the chat facility to ask questions at any time during the webinar, but they will be answered after presentations from 1:30 onwards. If some questions cannot be answered, we will forward your questions to the speakers to send their answers by email. Just a few words about our project. As you can see on this slide, these are the infrastructures that our project is really supporting and trying to identify links between different low-carbon infrastructures and how there might be some benefits regarding reduction of costs or better efficiencies by connecting different low-carbon infrastructures. If you are preparing or would like to prepare a proposal for an application for funding from EU, UK or Scottish Government funding programs, please do contact us and we will connect you with researchers who can assist you in developing a research proposal and submitting the application. So today's webinar is about sustainable landscaping and water engineering. That means really linking two of the areas within the scope of our project. And the speakers are Anita Meldrum and Slobodan Mickovski, and they are both academics here at Glasgow Caledonian University. Welcome, and I will kindly ask you to start your presentations.
Thank you. I'll be the first one to start today. My name is Mickovski, Slobodan, originally, as Branka introduced me. And I'll be happy to talk to you today about the sustainable design with vegetation. That's the marriage of civil engineering, if you like, and biology and plants. So vegetation in general. What are the main thoughts we have when we start thinking about using vegetation in civil engineering? The main idea is to give an engineering function to that vegetation, which will be additional to the aesthetic and environmental benefits we get anyway from the vegetation. So whatever I'm going to talk about today applies not only for landscaping, but also for any infrastructure design, any design that involves civil engineering, any design that involves stability in the first place. I'm going to talk briefly about the reinforcement function of vegetation that might have for the soils, and I'm going to talk also briefly about potential of using vegetation in rainwater harvesting through the application in green roofs. The engineering part of the engineering function of vegetation in soil reinforcement will be concentrating on the mechanical and hydrological effects of vegetation. And then I can talk about the stability of vegetation, or why do we want a stable vegetation in order to have a sustainable and resilient engineering structure when vegetation is involved. And then I'll talk briefly about the design measures and approaches we use when designing with vegetation, a brief case study on the subject. While as for the green roofs, I'll talk about the sustainability benefits of them, which I'm sure most of you are familiar with, and brief you on the results of a lab study we did on using sustainable approaches when designing green roofs. So let me start with a brief definition of the term eco-engineering. This is the area I've been doing my research in the last 15 years. Eco-engineering is also known as eco-technology, also known as ground bioengineering. As I said, it's a marriage between civil engineering or geotechnical engineering and plant science. In other words, we are adding the effect of plants or their below ground parts into the mechanics of the soil that they inhabit. By the definition, eco-engineering is the proactive design, management, and restoration of sustainable ecosystems which integrates human society with its natural environment for the benefit of both. Quite grand definition, but what I'm going to talk about today is the effect of this eco-engineering on civil engineering and vice versa, the effect of civil engineering practices on using the vegetation. It is my belief that this is the ideal approach for urban landscaping, if not for great infrastructural use. Why? Because it is a problem driven. Every design we do in civil engineering stems from a certain problem. Similarly, here we have a problem with unstable soils, compressible soils, soils that fail, and we need to solve that problem. The difference here is that we are providing the green part of it. We are using a soft approach in addition sometimes to the hard engineering approach, and we are providing the green benefits of it. We're providing sustainable solution for a problem. We're also providing cost-effective, eco-friendly, aesthetic approach and solution, which ultimately lead to enhancing of biodiversity, but also resilience of that structure in the long run. In this case, vegetation is tasked with performing multiple functions. So on top of their engineering function, which would be my original concern for stability of the structure, it performs also biological function, which is evapotranspiration. So taking water out of the soil, evaporating it, makes the soil more stable, for example. Also, additional to this, ecological benefits like enhancing the biodiversity are also performed. But last and not the least, for landscaping, you have the aesthetic benefits of the vegetation. So where is the engineering function of vegetation visible? We consider vegetation from civil engineering point of view as a nuisance in general. That approach has to be changed. We are working on an engineering approaches that have to be inventive, all-inclusive, and it have to be sustainable and resilient. So vegetation for us engineers is good because it provides structural stability. We consider the roots as biological soil nails, basically inclusions into the soil that keep the soil stable and prevent failures. Bigger roots can be also seen as micropiles. As you might imagine or you might know, piles are structural solutions used in geotechnical engineering to provide stability of foundations or stability of earthworks. The roots can perform that function as well, given proper size and proper distribution. The effect of vegetation on soil reinforcement is quite active and quite visible, especially when it crosses potential slip planes. So providing a solution against landslides, for example, very shallow slope failures. Another one, as I mentioned earlier, is the soil moisture control. Via evapotranspiration, the roots extract water from the earthworks, from the soil, and thus increase the stability. The biggest enemy of the soil in stability sense is the water. If we manage if we can manage to properly deal with the water in the soil, we have a stable and resilient solution. Also, vegetation provides erosion protection in terms of interception, infiltration, and flow attenuation, which is quite valid and quite applicable, especially when we know that we are facing effects from the climate change. In one sentence, it's a complex system. Vegetation and the soil, it's a complex system, but it has its limitations. In other words, it's limited to the depth that roots can penetrate into the soil. As far as they can go, they can protect and prevent from landslides or erosion, but not deeper than that. How do we do quantification of these effects? Usually through laboratory and field studies, we do mathematical quantification, and then we do modeling of this vegetation before we actually apply it. For example, on the left-hand side of the slide, you see purpose-built machine laboratory equipment where we tested the strength that roots give to a particular column of soil. In this case, we had willow plants with their roots passing a potential shear plane, and we realized that when sheared, the soil is quite stronger than it would be when it's fallow, when there are no soils. Similar type of experiment on the right-hand side we performed on a number of locations. This particular one in China, so in traditional Chinese forests where a lot of landslides occurred. We tested the strength of the root permeated soil with field equipment, and we also measured, in the same time we measured what's happening with the pore water pressures in the soil, in root permeated soil. What we realized is that there is a change in pore water pressures, which can lead to disturbance of the soil, but vegetation is able to deal with this. This is the visual representation of the results we got from the laboratory and field testing. The upper line shows the rooted soils, providing quite a lot of strength and quite a lot of reinforcement, while as the lower blue line, if you like, shows what the strength of the soil would be if there was no roots involved. Anything in between is classified as reinforcement provided to the soil by the roots in itself. So as you can see, it will be quite significant, and it will vary with the number of roots that potentially cross the shear plane. It will depend on the type of vegetation, type of soil, etc. What happens to the soil moisture when we're doing the tests, or when we're testing the vegetation? Increased evapotranspiration by the vegetation in general can cause a significant improvement in soil strength because it increases the so-called matrix suction. In other words, the suction that keeps the soil together and provides the strength of this soil. So on an experiment here of a colleague from Strathclyde University, you can see that different types of soils permeated with different types of living roots can have quite varying strengths. So silty loams, clay silts of different behavior, these are all typical soils from Glasgow and Scotland, can have increased soil strength down to anywhere where the roots permeate. So 2 meters, 4 meters, even down to 8 meters, there is a small but also visible strength increase in the soil because of the roots that evapotranspirate and increase the matrix suction. At this moment, we are doing a PhD research on this subject, so we'll be expanding on the behavior of the roots under hydrologic conditions. In order to have stable soil, we need to have stable vegetation on it. We are all witnesses to what's going on in our parks. These photos have been taken in Pollock Park in Glasgow back in 2011, and I'm not showing anything newer, although I have several new things that happened over this winter. Basically, we're all seeing vegetation being overturned and stopping to perform its function. Not only the vegetation is dead, but it stopped from performing an engineering function. And I'll draw your attention here on the left-hand slide. See the bottom of that overturned tree, or see it here. What you see is basically water ponded. So at the bottom of the root system you have ponded water. The effect of that water is that it softens the bond between the roots and the soil. So when the wind is applied to the tree, it acts as a sail, basically, the tree, and just overturns. Why? Because there is no bonding strength between the roots and the soil, and the water is the main contributor to this destabilizing effect of destabilizing effect for the vegetation. So you might have seen the shape of the root system here. It's quite thin, quite shallow. This combined with the ground conditions, which is high groundwater, basically contribute solely to the instability of vegetation. We need to be quite careful with it. So a selection of proper species, selection and amelioration of the soils where they have to be planted, as well as regular maintenance. We can specify all of this in order to have healthy vegetation, stable vegetation that will perform the function we are requiring from them. These are the, you can see in a close-up, you can see the effects that the water has on the roots. It's basically quite dark, it's blackened, and can't grow through the groundwater horizon. We have quite a lot of experience in this subject. I've published on overturning of trees. I've published on urban parks and forests and stability of the trees in such parks and forests. And we can help solving any problems you might have in more detail by providing engineering approach to it, providing quantification of the effects. What happens then once the vegetation is down? As I said, it's not good for the soil, it's not good for the engineering practice at all. The roots which are left in the soil, which have been broken during the breakage, are left in the soil and start to decay. Once they're decayed, they basically provide holes through which water can percolate. The soil is not stable, will be behaving like a sponge. So in after something like 10 years, you will see there is a critical drop in the strength of the roots, which basically destabilizes the soil. This is an area of good interest, and I'm happy to hear about proposals or anything that can be turned into a viable and applicable potential research in terms of quantification and risk management. More details on the subject you can find in a book that we published with a number of colleagues in 2008, 2009. We propose a range of eco-technological solutions, and we're trying to change the attitude, to move the attitude towards matching the engineering solution to the problem by using local or native species, and apply the solution in an engineering fashion, so it's quantified and it's monitored during construction, etc., but also includes maintenance over the long run. We're also advocating a combination of hard and soft engineering. Number of potential solutions that we applied in the past, you can see here, taken out from the book, basically application in different places, in different circumstances, whether it's embankment protection or it's riverbank protection, etc. A brief case study, some of you might be familiar with potential for slope failures, that is putting lives at risk in Stonehaven. This is the famous Burvey Brace, a slope that has a history of failures, and here we had an input with Jacobs for Aberdeenshire Council. What we did, we provided structural stability using traditional engineering methods, and then we provided resilience in the long run with proper drainage management for the whole slope, and then the erosion protection by selection and planting of different grass and tree species that will increase the roughness and encourage infiltration of the rainwater. And we increase the biodiversity of the whole area, because it's a protected area, again by a proper selection of the species and the methods employed into this. We consider vegetation as part of an integrated, resilient design which has to be sustainable, but also comprised of vegetation which is stable on the slope or on the soil where it grows. And in the next few slides I'll be talking about the research we've done on green roofs and walls. Considering the engineering application of vegetation, we can build steeper slopes for our green roofs. In a previous slide, you might have seen a house that is being currently built in France that is basically a slope of more than 60 degrees, and it's a green roof. So traditional green roofs, for example, like this one here, which is in Basel, in Switzerland, where you don't even see that it's a green roof. It's basically a flat roof cover over a car park in Basel, or something which is ultra steep, like this wall for the London Olympic site, or something that has variable steepness, like the ocean terminal in Vancouver. If this engineering function of the vegetation can be coupled with sustainable practices like rainwater harvesting, we can ensure that the peak flow from the rainfall is attenuated. We can use recycled materials into it, and we can reuse the water that comes onto the green roof. And this is all on top of the ecological benefits, like increasing biodiversity. So the research we've done was a laboratory study. Basically, we used recycled construction waste as a substrate for our plants. We planted traditional green roof species like sedums and grasses under different state of maintenance, so short grass and long grass. And we saw first that the strength of the soil significantly increased under grass. So grass has quite a lot of roots, quite wiry roots, strong, and it increases the strength. This allows us to build the green roofs at a very steep slope. Then we looked at coverage. We can provide a total coverage of the green roof in, let's say, 2 weeks. That's magnificent, especially with the fact that you're stopping the erosion in those 2 weeks while the vegetation is being established on the roof. And thirdly, and basically very important for urban design for resilience, is attenuation of the peak flows. The vegetation was able to attenuate quite a lot of the peak flow, and they basically distributed over into through the drainage, of course, into a system that allows reuse of the same water for non-potable purposes within the building. So we would like to expand on this research and see the viability of it and the whole life costing of the whole idea of reuse of water and reuse of civil engineering materials. Part of integrated design, as you can see here, is a bit of an interesting cartoon which tells you where the integration of different parts, or where is the resilience in the design. The cow that goes down the green roof, what's the benefit for the guys underneath? They get free milk from a free-range cow. So that's the approach we're looking for here. On top of the stability of the green roof, which will have to be assured, will give a bit of sustainability and cater for the environmental concerns. The problem environment, as you might imagine, is huge, and we are trying to concentrate on the core of it. So vegetation is not a universal solution. It's not the silver bullet. It's only effective down to the point where the roots stretch. The idea is to use naturally variable material to perform an engineering function. So we are catering for the environmental, social, and economic benefits. And the approach has to satisfy the engineering functions like stability, but also environmental, societal, etc. concerns. We include all the phenomena on the soil, water, and air interface. We do a holistic approach, and we think this is what makes our research and GCU group quite unique, with the fact that geotechnical engineers here lead a multidisciplinary team that caters for several other disciplines. With this, I'll thank you for your attention and pass the baton on to my colleague who will speak more in detail about water management.
Hi everyone, I'm Anita Meldrum. I'm going to talk to you today not about the whole area of water engineering, because that's far too vast and complicated even for me to get my head around. But I'm going to talk about two of the areas where we're doing research at the moment, and which we are building then back into our environmental civil engineering teaching. And that involves water resource management in the developed and developing worlds. If I can get this to work here. First, looking at the developing world, and if you attended the last webinar, the speakers were talking about this, and I'm going to focus on one aspect of it, which I'll explain to you a little bit in a minute. What we're trying to do is to manage flood risk sustainably. And that basically means trying to return to a more natural solution to deal with the fact that we have messed up the water cycle by putting a lot of concrete structures for our cities, which is great for us because we're not walking around in mud when it rains, but it does mean that the natural environment is not able to engage in doing its natural function of infiltrating and evaporating the water away from the surface. So this is a particular issue. So I'm going to talk about water sensitive urban design. So that's design that integrates water into the urban landscape. So this diagram expresses it quite effectively, I think, and it's taken from Melbourne Water, who were the people who started doing water sensitive urban design because of their issues getting access to water in the Australian urban environment. If you look at the part of the slide on the left, you'll see what happens in the natural water balance. We get the big blue arrow shows the rain coming down. The arrow going up next to it shows what happens when we have the natural environment, where we've got trees and greenery evapotranspiring and putting water vapour back up into the atmosphere. And the arrow going down shows water from rain infiltrating into the root systems of plants and perhaps even down into the water table. The small little blue arrow shows you the natural urban runoff, which is about 5% of the rainwater. If we come to the urban environment with all our concrete structures and hard surfaces, you can see that the runoff becomes about 95% of rainfall, and it runs straight off into our surface water drainage systems and on into rivers. And this is why we have floods. Those natural mechanisms that allow water to infiltrate and water vapour to go naturally back into the environment are stopped. And the aim of water sensitive urban design is to think about water balance and try to reintroduce green measures back into the city environment. And you can see from that, if you look at the blue arrow in the middle on the right, actually, if I press that, I can get the little arrow. Sorry, I forgot to do that. If you look at the little arrow on the right here, you can see that that runoff is markedly reduced by trying to reintroduce more natural systems of flood attenuation into the urban environment. And the point of this is to do several things in the cities. It's to make cities more resilient. Whenever we have flood situations, it has a dramatic impact on lives, and we're seeing that at the moment with the flooding down in the Somerset levels. People lose their properties, or they lose access to their properties for long periods of time whilst contamination is removed and the house is replaced to its original condition. The value of their properties reduces, they can't get insurance, their whole lives are quite disruptive. And for businesses, particularly if they're in food or beverage type environments, the product can be contaminated and they might not have access to their production facility for some time. So by trying to bring this more natural type of environment back into the cities, we're going to help to contain those issues. Of course, those issues are also exacerbated by climate change because, we're in the west of Scotland, the weather here is getting warmer and wetter, and that's because the climate is